Here is our first example outside of the discussion on how to work with vectors mathematically, but our first example in using vectors to find a solution. So we have these three vectors, vector A, vector B, vector C. This one's a little different in that we know what the answer needs to be. So this is essentially telling me that the resulting answer has 0 x component, that's implied because there's no I hat term, plus the 2 j hat component. So similar to what we were doing in the video about working with vectors mathematically, it is still true that the x component of this resultant vector, this 0, is determined by adding the x components together. It does not matter how many vectors we have. In this case, we have 3, so we just add the x components of all 3 vectors. The y component of the answer comes from adding the y components of these 3 vectors together. All right. In this particular case, vector A is really easy to write. It points all in the x direction, which means there is 0 y component. Technically, we don't typically write the 0, but as we're learning how to work with vectors, sometimes it can be helpful to do so. Vector C here points only downwards. That means there's no x component at all. And then we would say for j hat minus for j hat, the negative sign to mean it points downwards in the negative y direction, and then the 4 represents the length of it. In this particular case, we are asked for vector B. We don't know how long it is. We don't know what angle it points at. But we can say vector B is going to have some sort of x component. I'm just going to call that B sub x. And some sort of y component, according to the picture anyway. So plus by j hat. To come over and plug in, this represents that we add all the x components together of all the vectors we're adding, and those together determine the x component of the answer. So that's what we're working with. In this case, we know there should not be an x component in our answer. And that was what we found out by looking at what the problem said. A plus B plus C vectors are equal to just 2j. So no x component. The x component is 3. Technically, positive 3. We don't have to write the positive, but again, sometimes it's helpful to write the positive just to know that you are definitely accounting for the direction. So positive 3, we know vector A has at least a component that points in the positive x direction and a length of 3. Vector B, we actually don't know. And we're going to just put that in here as what I called it over to the side. We just said it has some sort of x component. So I'm going to leave that as a B sub x. Vector C also does not have an x component. You don't technically need to write the 0. But again, just for explanation's sake, I'm doing this. So this now is an equation that we can solve for bx. If we take the 3 to the other side, we find that vector B needs to have a component. The negative means it needs to point to the left, and then it needs to have a length of 3 in order for us to get this result the problem asks for. Now we're not done. We need to account for the y component of B as well. Y components, it's very similar. We're adding A, B, and C again, but specifically the y components, the vertical components. When we add the y components A, B, and C together, we get the y component specifically of the answer. We know this needs to be 2. That's what the problem tells us. Technically, the positive sign is implied. If you want to write that as the positive sign, just so that you know what we mean by the direction, that's fine. Vector A does not have a y component. Vector B does. We're trying to figure that out, so I'm still going to just leave that as a B sub y. And then vector C, its y component points down with a length of 4. This gives us a nice little equation to solve. If I take the 4 to the other side, the y component of vector B needs to be 6. Technically, the positive sign is implied there simply because it's not negative. So looking at these, in terms of vector notation, we could say that vector B can be written as negative 3i hat plus 6j hat. This is one way to represent the vector. Now, the problem doesn't specifically state magnitude and direction, but to describe what we see in this picture as vector B, it would make sense to describe that as a length and an angle. Now, it's not drawn to scale to meet this answer. We just need to think of vector B in the given picture just to represent the general direction. But let's go ahead and take it that step further and describe this same vector in terms of its magnitude and direction. So the length of the vector and the angle it points at. Again, I highly recommend drawing out what your answer means. So our answer, vector B, points to the left by 3 and up by 6. So vector B itself points up and to the left. Having this nice little triangle makes it really easy to remember. The magnitude is Pythagorean theorem. And then the angle, I'm just going to talk about this angle for just a minute. The tangent of that angle would be 6 over 3. So inverse tangent of 2 would be 63 degrees. Let me go ahead and find the magnitude while I'm at it. .7. Technically, we should just have 1 sig fig. In terms of magnitude and direction, our answer, in terms of 2 sig figs, which I've written at the moment, I'll round it to 1 in just a sec. So the length of it is 6.7. The 63 degrees is here, but again, if we want to just describe the angle, we need to start at a positive x-axis and move counterclockwise. So I would take 180 minus 63 degrees. In 2 sig figs, it would be 120. Technically, we have 1 sig fig, which on a test problem, I don't like leaving you with just 1 sig fig, because 120 is very different than 100. But I will, as long as you're within 1 sig fig of what it needs to be, or should technically be, I'm going to give you full credit if you have the right answer. But I do want to see that you're putting some thought into the significant figures. So this is one example of a vector problem. Again, this one isn't representing distance or position or velocity. They don't assign any units to it, but that's okay. This is how we work with anything that is a vector.